Alright everyone, this is Saba. The topic is right there. I'm pretty sure you know it already, that's why you're here. Who's going to better introduce yourself? Take it over.
Hi everybody, thank you so much for coming to my talk. Today I will be talking to you about optimizing some code from a latency and memory perspective. I'm a data engineer at NYC, which is a hedge fund here in New York City. And let's first go over what we will be covering during the talk. We're going to start with the problem that I was trying to solve and what I was trying to do. Then we'll go over the problem that we faced when the code was pushed to production. We'll go over some ways of analyzing the problem and understanding the problem a little bit better. Then we will attempt to iteratively solve the problem and then see how close we are to an actual solution. And then hopefully we do with some lessons we can take to your everyday. So let's start with the thing that I was trying to do. Imagine you're a research scientist and you have written up a paragraph or a report. What I'm trying to do is tag themes from that report. So let's say you're talking about the general economy and labor outlooks, economy and labor outlooks are the things that I'm trying to extract. So let's say you're writing a tool. What I want to do is incorporate this inference, this machine learning theme tagging process into your workflow. The reason that I want to incorporate this into your workflow is because it's quite rare in machine learning to have a true label, right? So let's say I have a machine learning model that predicts with 90% accuracy, then the accuracy of that label is with 90% confidence. And so if I incorporate this into your workflow, and you as the expert on the topic confirm that this is the true label, this is quite rare, and I will assume that then I have 100% accuracy in my prediction. And so that's what we're doing here, right? So this is the tool that you generally write in, and we're incorporating this into your tool, and the reason we want to incorporate it is so we can capture the true label. But obviously that introduces a requirement, and the requirement is that we want the code to be fast, right? You're a research scientist, your time is very valuable. I don't want to waste your time sitting behind this inference code running before you can do me the favor of confirming the true label. Some motivation before we spend 40 minutes talking about this topic. In generative AI applications, enhancing metadata of a text with entity extraction or with theme extraction is going to help you with retrieval and search capabilities. And so this, and the fact that we're capturing the true label for the themes for this body of text is going to help us with future applications of GenAI on this corpus of data when it comes to retrieval and search. So let's start with the system design diagram for this tool. We've talked about how it starts from the user's screen. So you've written up your report, you click the button that says, hey, go get me the things. That then is our fascinating endpoint, which runs our tagging process. Then the prediction is saved somewhere, and then the prediction is also displayed out to your screen to the user. So here's sort of like the benefit of getting a true label. You get to interact with the prediction, promote it or demote it based on how accurate it is, based on your expertise with the data. Obviously, that is really important. We want to see that output, and that output is ultimately going to help us in the process. There's space in the microphone. Can you hold the microphone up a little bit? Yeah. So we talked about wanting to make things faster for you as a research scientist, right? So between the time that you click the button to receive the themes and you getting the themes displayed on the screen, that's the part of the process that we want to optimize. We want to make sure that you're waiting for the least amount of time possible. And so that's that part of the process there. So let's talk about the infrastructure behind the tool a little bit. We don't have a high number of requests per second. This is an internal tool that we're using, but we do expect to get multiple people using it at the same time. And what we want to do is to make sure that one user getting the themes is not blocking another user and is not wasting extra user's time. And so to prevent that from happening, we have utilized a load balancer and then balanced the different requests between a number of EC2 machines. And so the latency requirement here comes from the fact that we really just want to save that resistance very high. So let's talk about the inference process. So we have that body of text that you've written, and we want to run some prediction. This prediction happens at a sentence level. So this is going to be important. It's going to come up throughout the talk, that the prediction is going to take place at a sentence level. And so first we take in, let's say, that paragraph. We break it up into the sentences. You have your different sentences. Then we run a prediction per sentence, and then we aggregate the results to get prediction at a paragraph level, and then we return that to the user. So the models that are used in this tagging process, we're using multi-labeled classification models. So these are classical machine learning classification models. This is not an open-ended entity extraction problem, and there are no elements used. Right. So let's take this a bit further. So what I mean by classical classification model is one example is a logistic regression model, and we are trying to tag to a priori known themes. So we'll sit together and know the kind of content that we're going to be writing here, and we'll decide, hey, these are the 20 themes that I want to tag to. So the number of themes are known ahead of time, and the themes are also known ahead of time. Let's get into highlight. And so in this case, this is what we're doing, and these are the two different models that we're using in this process. So the first one is an embedding model. So obviously you have your unstructured text that's coming in. We've broken it up into sentences, you have your sentence, and then you need to embed it into the embedding space to get some structured vector that then we can run prediction on. So we're using E5 base for this, but you can use any embedding model to take it from the unstructured text that it is to embedding. And then we have our embedded vector, and now we want to run classification. So in the base space, a logistic regression file is a binary classification model, right? So if you had only one theme and we wanted to see if the sentences had that one theme, in base case, you're getting the binary classification, so is it this theme or is it not this theme? And you get some probability between 0 and 1 for the confidence on that theme prediction. Now, if you extend this to the nth dimension for those n categories, then you have a multi-label pattern. And so these logistic regression models are ones that we had trained for our use case, given the themes that we were trying to tag. So let's go back to the problem, right? We pushed this code to production, and the code is just too slow. The entire goal was to make this fast, so that the valuable time of our research scientists is not wasted as they help us tag to the true data. And so for the purpose of this talk, I will be using some data from the September Fed Reserve transcripts, in particular some fraction of the first 2 pages, which gives me about 25 sentences, and I'm trying to tag those 25 sentences. Now, I don't expect my users to be writing this many sentences. Generally, it's in smaller chunks that we try to do the tagging. But if we solve for this problem, and if we speed up for this problem, then the rest of it will be fast as well. So running this on the first 2 pages of the Fed Reserve transcripts, these are the themes that we found. So labor was 99% accuracy, labor cost was 80%, so on and so forth. And so if you read the first 2 pages, or if you don't, these themes more or less seem relevant to the text that we are adding on. And so it's important to keep these tag themes as we iteratively hope to solve the problem as we make things faster. We don't want the accuracy of the output to be impacted. So we'll be coming back to the results because we don't want the results to be impacted. So we've talked about running prediction at a sentence level. Now this obviously begs the question, what is a sentence? How do you identify a sentence, right? And so one basic answer is just take a period and break on the period. But there are things that fall outside of that. So if you have any kind of fractional percent or any kind of fractional number in your text, when you break on the period, you're misdiagnosing what a sentence is. You can kind of solve for this problem and say, well, I'll break on period and then space to identify a sentence. there's still examples that fall outside this rule. So US space economy, which actually shows up in the text that we're looking at, falls outside that example. You may even solve for this problem and say, well, I'll break on period, space, and then a capital letter, and then I'll tell all my users, hey, follow this rule. Or you can do some custom cleaning. The takeaway here should be that there are some trivial problems, such as I have a paragraph, I want to break it up into sentences, but it's not as simple as it seems. And in our case, we just used a heuristic that worked well for our input data. So let's go back to the problem. We have our process, we've gone to the design, and the code is too slow. And we want to solve for this problem. We want to iteratively make the code faster. And there's some amount of work that we're doing. We know that we've got to embed the sentences in the embedding space, and we need to run prediction on the embedded sentence. And because the texts are not known ahead of time, this computationally heavy work just needs to happen during runtime. There's none of this work that we can do ahead of time. We're also using Torch in some pre-trained models. They're well tuned to accept large amounts of data, and so trying to speed those up seems like a waste of time. And so let's focus on energy on not doing any other kind of work that we're doing. So the embedding, the prediction, the computationally heavy work needs to happen during runtime. None of that is known ahead of time. And so let's try to remove any other bottlenecks. So for this purpose, we're going to cprofile the code. Now, cprofile is a Python profiler. What it helps us do is get an understanding of what functions are called, how long it takes for those functions to run, how many times we call those functions, and save the output. And so cprofile is going to be able to profile any code that you have in the context manager. cprofile is a part of the standard library, and you don't need to pip install it, and it just comes in the standard library. Similarly, pstats comes in the standard library, and so let's kind of interact with the data that we got from cprofile and see where we're spending our time. Let's try to find those bottlenecks that we're trying to solve. There's a lot of data that comes out of cprofile, and you can look at it different kind of ways, and you can analyze the data in many ways, but two ways that we're going to look at the data is by sorting it over total time. And so sorting it over total time gives you the single most expensive function without any child calls. And sorting it over cumulative time gives you generally an idea of where you're spending your time. This includes child calls and is recursive. And so if you sort by cumulative time, the top function that you'll see is your main function. So let's take a look at the output of cprofile for this first version of our production code. Expectedly so, in the top line, we're spending some time encoding the sentences that came in. That's expected. We knew that we had to spend time doing that. But we're also spending a lot of time loading in the model. So you'll see that in the first one, the second 4 lines. There's some more loading models in sentence transformers. We're spending about 17 seconds there, and we're actually calling that 96 times. Similarly, we're spending quite a bit of time, 10 seconds or so, on 41 calls in Vodapore. So Vodapore is a package that interfaces with S3, and we know that our logistic regression models are saved on S3. So this cprofile is both showing some bottlenecks, but also surprising results. We're learning that we're doing a lot of work, loading in a lot of models that we did not necessarily expect to do. And so let's go to the process, as sort of like the state of affairs at the time. So given the results from cprofile, we learned that we're not only loading in the models every time at a sentence level, we're also downloading them every time. So the reason that you see 96 loading in models for sentence transformers is because you're loading in that embedding model the number of sentences. So at a sentence level, we were loading in the embedding model a couple of times, and also we were pulling in the logistic regression models at a sentence level every time. And so obviously, let's go back to our wanting to spend valuable time of our researchers doing the work that we can't do ahead of time, the computational work. This really does not depend on the input data. We can do this work ahead of time. And so the first step in making this optimized is to remove that from the critical path. So we know that our models don't change at all. In fact, they shouldn't change because we want robustness and trust in our outputs, right? So the embedded model needs to be the same every time. Our prediction models shouldn't change because we don't want our answers to change. If we run the same process twice on the same paragraph, we want the same output. So the models don't change at all. And what we can do is we can download them once and load them in once and share them. So we can completely remove this from the critical path the user receiving the response. And so here's a solution that maybe you can take to your everyday, or if you have a similar situation. Before the start of your application, you can download these models to a local temp directory. You can do this for sense embeddings. You can do this for any classification model that you have, or any NLP entity extraction, such as Claire or Spacey. You can download it to a local directory, and then you can load from there and share. So let's see how this impacts our results. We went from about a minute to 20 seconds. That's a 61% decrease in time, which is pretty good, but it's still not great. So let's see if we can do a little better than that. So again, we'll pick up the process for how we did it before. So we'll start with cProfile, and let's take a look and see if we're doing anything that's unexpected or any bottleneck here that we can remove. So looking over on that line, we're just doing some more S3 stuff. This time we're putting some objects on S3. We're calling this one 41 times as well, and we're spending 14 seconds doing that. And so let's go back to our process. We were saving our predictions, and it's important for us to save our predictions. So let's say one of my users comes to me and says, hey, this tool, the prediction doesn't make any sense at all. I would want to go back and see which model is giving me the wrong prediction. So I want to save these predictions. But what we learned from the outset of cProfile there is that we are saving the predictions at a sentence level again, because we're calling it 41 times. It's also in the critical path of the user getting the response. So we're saving at a sentence level before we aggregate the results and return it to the user. So there's really two main things that are wrong with this. First of all, we really don't need to save the prediction results at a sentence level. You can accumulate all of them and save them in one go. But even more than that, you don't need to do it before you return the results to the user at all. So for this purpose, you can use a fast API background task. And so this is code that will help us do that. So we're going to use a background task object and add writing of the data as a background task. And in that way, remove it from the critical path of the user receiving those time results. And so this is what we were doing. So save predictions was there in the critical path, and we've removed it from the critical path. And so now the users are getting the responses before the predictions are saved. So now we went from about a minute to 5 seconds, which is pretty good, 90 or so % decrease in time. Let's again see if we can do better for our users. Now we've talked about different aspects of this diagram. We downloaded the models ahead of time, and we're pulling them in ahead of time. We're saving predictions after the user gets the responses. But there is this tagging process that we haven't really talked about. And let's see if we can optimize the tagging process. So what is the tagging process, Shirley? We talked about wanting to break the paragraphs into sentences and predict at a sentence level. So that's the first step. Then we embed all of those sentences in the embedding space. Then we run our classification models, this is the prediction step. And then we aggregate the predictions and return to the user. And so each of these steps depend on the previous step, right? I can't predict anything if I haven't embedded my And so let's first start with working on running the embedding piece. And if we can speed that up, then the entire process will be sped up. So I will be working on some benchmarking on embedding in general. And so for that reason, I want a text that has a lot of sentences, and the content of it really doesn't matter to me. So I'll be using lorem ipsum. And for those of you who may be worried about the embedding speed being impacted, whether it's the Federal Reserve meeting notes or lorem ipsum, fear not, it does not impact the embedding speed. So let's go back to this diagram that we've seen a couple of times. We know that prediction happens at a sentence level, and so embedding needs to happen at a sentence level. And one way we can do embedding for end sentences is we can do so in sequence. So we first embed the first sentence, then on to the second, and so on and so forth. In that situation, the end sentence is waiting for all the sentences before it can be embedded in the embedding space. Another way to do that, and this diagram alludes to it nicely, is we can do so in parallel. So these sentences really don't have anything to do with each other when they're being embedded, and they all share the embedding model that is unchanged. So we can use multiprocessing to embed these sentences in parallel, and the hypothesis here is that that would be faster, because in that situation, your end sentence is not waiting for all the other sentences before it can be embedded. So now let's go run some experiments and see if that actually happens. So first, let's embed all of our sentences in sequence. In the worst case, it takes 4 seconds, and expectedly so this is linear. Let's go to our solution for parallelizing. This does not look very good. So first of all, it takes 50 seconds to embed in the worst case, and also this doesn't look very parallel. So what you're seeing over on the right is what true parallelism looks like. So you expect to see this functioning. So there's some sequential execution. On top of that, it's even worse than sequential, and this was our brilliant idea, and so there's some kind of locking happening as well. So let's go back to our favorite tool. Let's see profile the code. When you see profile outside of multiprocessing, this is what you see. So what you're seeing is that you're waiting for the processes to finish. And so if you want to see profiles in multiprocessing code, you need to profile inside of the process. And so this is what the top section of this page is showing. That's C profile inside one of those processes. And basically in parallel, showing what's happening under the hood when in parallel, I'm embedding one sentence. Now I wanted to compare that to what actually happens when I embed one sentence in sequence. Because what I'm trying to understand is why is it that in the parallel case, embedding one sentence seems so much longer than doing so in sequence. Now, comparing the outputs, the functions that are being run are the same underlying torch functions. They're not in the same order because this is ordered by total time, and it's taking different amounts of time, so the sorting is not the same. But ultimately, the same torch functions are called. And so this leads me to believe that there is something about multiprocessing that's leading to the underlying torch functions to lock up and for the embedding to take longer. Digging in a bit more, I learned that Torch has its own thread pool that implementing parallelization on top of is necessary. And so if we want to run parallelization on top of Torch, we need to limit Torch's number of threads before we can implement parallelization on top. And so if you want to go back to our previous experiment and get actually good results, we need to limit Torch's number of threads. But moreover, the conclusion here is, I don't understand why we would try to do that, right? Why would we try to do the thing that Torch is powerful in doing, which is taking in a lot of data and embedding them in parallel? Why would I try to limit it only to implement parallelization? And so we'll kind of experiment with that in a second. And more so, it'll be less code for us to let Torch handle it than try to limit the threads and implement our own parallelization. But to make sure, let's go back to our previous example. So this is limiting Torch's number of threads to 1. Now, in the worst case, it takes 1.4 seconds. Okay, great, fantastic. So parallelization works in this case. Things are not perfectly parallel, so there's still some sequential execution happening. And I'm using 11 processes here because I'm running on a 12-core CPU machine. But let's go back to the lesson that we learned. So we want to use Torch's power for the embedding. And so I have a list of end sentences. I just want to embed them in one go. My embedding model has an embedding size of 768. And so in this situation, my output is going to be of size 10 seconds to 768. So running the benchmarking results, again, in the worst case, things take 1.2 seconds, which is gain from the previous example, but in the case where I have fewer sentences between 0 and 20, there's quite a bit of gain. So in exploring ways of speeding up embedding, I also experimented with embedding the paragraph with end sentences all in one go. Now, obviously, our problem and our original design was embedding per sentences and predicting per sentences. But in our exploration of wanting to speed up embedding, let's try this out as well. If you embed the entire paragraph as a whole, because there is really no distinction between sentences, what you get is just a vector of 768. And so this is the benchmarking results for that. In the worst case, it takes 0.4 seconds, which is quite a bit of a gain, and that's rather expected because instead of embedding a matrix of end sentences by 768, you really only have a vector of 768, and so embedding that is faster. The other thing to notice from this plot is that there is some plateauing going on after a certain point. So let's try to understand what that is. So the E5 base model has a token limit of 512 tokens, which is about 25 sentences, which is around where we're seeing the plateauing taking place. So now we've discovered a way to do embedding the fastest relative to the previous versions of embedding one sentence at a time. But let's put a pin in that and we'll come back to this because this is really not the problem that we were trying to solve. And so let's compare all of the different ways we've embedded and done the benchmarking results. So ignoring the bottom blue one, which we'll come back to, which does this at a paragraph level, the best option is letting Torch handle all of the end sentences in one go. And so given the optimization in the previous step in the embedding model, now we're going to take the learnings from this step and take it to the prediction step. And so previously what we were doing is we were running for loops over a sentence at a time. We were embedding one vector at a time and then predicting one vector at a time. However, given the fact that now our embedding sentences is in matrix form, we can take this vector operation to the prediction step as well. And in that way, predict all of the end sentences in one go and carry on with the vector operations in that. So this is a function that helps us do that. So what I'm interested in is not every single label per sentence. What I'm interested in is getting the top K prediction per sentence and its associated scores. So that's what this top K is, right? So let's say I have 20 categories, I have 20 themes, but I'm really interested in getting the top 5 prediction per sentence. And so that's what this top K is in this function. And so we talked in the previous step about the embedded sentences now being in the matrix form, being end sentences by 768. Our scoring model is that logistic regression model that we've been talking about. And so we're doing this all in one go in NumPy. So let's do some dimension analysis to make sure that at every step we're doing things the right way, but also gain some intuition with what we're doing in every step. So first, we're going to get the predictive probability using our logistic regression model on all of our embedded sentences. And so the output here is going to be end sentences by end categories. Now, intuitively, if you think about this, per sentence and per category, you have a probability of predicting that theme. So what I'm trying to do is to take the top K, right? I'm not interested in reverse sorting the themes based on the probability. What I'm interested in is simply the top K. So we're going to use arc partition instead of arc sort. And it's going to be a lot faster, specifically when K is much smaller than n categories, which in this case, we said 5 and 20. It doesn't make that much of a difference, but obviously as this tool grows, we might be wanting to score with a higher and higher number of categories, and so we have to implement this the correct way. And so NumPy arc partition does so by default, it gives you the minimum, and that's why you put the negative on the probabilities, because I want the highest probability. And I want the indices for which the probability is highest. So that's why I'm using competition. The output here is n sentences by n categories, but I want to take the top k, so I get n sentences by top k. And so now I have my top k indices, and I want to carry that through and take my top k themes, and then get the associated scores for those. And so the classes for my logistic regression model is of size n categories, taking the top k indices for those. I get n sentences by top k. And similarly, I want to take the top k scores, and I use those indices that I found on the predicted probabilities, and the output is n sentences by top k as well. And so keeping everything in NumPy arrays now has given us a compounding effect. So the optimization from that previous step has flowed into this one, and keeping things in NumPy array will set up the future steps to use vector operations in NumPy as well. So you may be wondering why I'm changing the type of classes to objects in that line. So for that, let's start with understanding what the previous type of scoring model classes were. So the classes were originally of type fixed with strings. And so NumPy, by default, keeps all elements in a NumPy array in the same type, and it requires that they be of the same width. And so the longest class, the longest theme that I had in my scoring model was of length 38 characters. And so NumPy, because it's monomorphic, kept all of those in of length 38 characters. Now this was kind of fine when I had n classes, so I only had my 20 labels, but I'm about to take this to n sentences by top k. And so that's going to be really huge. And so to add some memory optimization here, we want to change the type to object. In that way, copy those strings once and just keep 8 bytes of memory per object for the show. So let's tie it together, right? So we talked about how we optimized the embedding step. Now we optimized the prediction step, going back to the original problem of the 25 sentences in the Federal Reserve transcript meeting. We can run things down in about 3 seconds. That's a 94% increase in time, which is pretty good. But again, let's see if we can do a little bit better than that. So let's go back to this plot. Obviously, we have now run things the best we could, more or less, with embedding things and predicting things at a sentence level. But there's that other experiment that we ran that actually was faster, and so let's see what we can do with that. This is changing the problem that we were trying to solve, so we're kind of exploring to see what we can do if we ignore one of the requirements that we had, which is embedding things and predicting things at a sentence level. And there are other constraints that come with this. So for example, we know that our embedding model has a token limit of 512. And so if you are trying to embed a paragraph that's more than that using this embedding model, you're going to not be embedding the entire paragraph. But again, knowing my users, I know that I won't be going beyond about 25 sentences. And so let's see where we can go with this. And obviously, if this leads to perfect results, there's always other embedding models that you can use. If you're getting a lot of performance gain using embedding the entire paragraph as a whole, you can always use a larger embedding model, assuming that doesn't take away from the performance gains that you're getting. So we've been embedding and predicting at a sentence level. Now the suggestion is let's try out embedding the paragraph as a whole. In this scenario, you don't really need to break your paragraph up into anything. You're saving on that operation. You're running prediction on that embedded paragraph, and then there is no aggregation of the results. You just have your results, and you're displaying that to the user. So the performance is much better in this scenario. It takes about 0.3 seconds to do this end-to-end, which is about 100% decrease in time. And we get some tag themes over on the left. We'll kind of try to understand those tag themes. Important to highlight, though, now we're solving a different problem, right? Now we're embedding the entire paragraph as a whole, and we're predicting the entire paragraph as a whole, which sort of from an intuitive sense, you're doing it. And so let's compare the prediction results when we embed things as one paragraph to the original results that we had in the first place. So over on the left is when we tag at a paragraph level. Over on the right is our original results of embedding things and predicting things at a sentence level. So things are looking good for the first two labels. The paragraph embedding predicts labor availability, which the sentence level does not. And pricing, promotion, and financing have a higher confidence when done so at a sentence level rather than at a paragraph level. And if you think about this from an intuitive sense, that makes sense. Because let's say I have 25 sentences and there's talk of labor, et cetera, but I have one sentence that very confidently is talking about financing. And so when I predict at a sentence level and then aggregate to a paragraph level, it makes sense that I'm more confident about financing because I have one sentence that specifically is talking about financing. And maybe I have another sentence that very confidently is talking about pricing. But when I embed the entire paragraph as a whole, you're sort of diluting that one sentence that's confidently talking about financing, and you're capturing the theme of the paragraph as a whole. So obviously, this is an improvement for the problem that we were trying to solve, but it is a different problem we were trying to solve. The labels, both from a stakeholder perspective and your users, they have to treat the labels a little differently. They have to treat the confidence intervals a little bit differently. The reason we're getting so much of a performance gain is because you're removing a lot of the work that you have to do right from the start. So instead of taking your paragraph of 25 sentences and breaking it into those 25 sentences and doing a lot of work, you're doing a reduction of data right at the front. And so you're removing a lot of those complicated vector operations that you would have to do. So let's take it back to the beginning and keeping things even at a sentence level, we're down to 2 to 3 seconds. And so things are looking pretty good. In terms of next steps and whether there's other things that we can do to optimize this problem, we can continue to do the thing that helped us in the previous step, which is keeping the vector operations in NumPy instead of doing any kind of looping on our sentences and such. And so let's go over some main takeaways. Just go back to the beginning and sort of like the thinking around how we solved the problem. We iteratively sequenced our code, found bottlenecks and hotspots, and worked to either optimize those or remove them if they did not depend on input data. And so this is a strategy for iteratively speeding up code. And so we found hotspots and removed them, namely with pre-downloading the models, loading them in once, and then also saving predictions after the user has gotten their answer. Another takeaway was letting packages such as Torch and NumPy do the thing they're best at. So in the Torch case, instead of limiting the number of threads and then implementing multiprocessing on top, let's just let Torch handle all of our sentences in one go. And similarly, let's let NumPy handle our vector operations instead of looping over our sentences one at a time, embedding them one at a time, and then predicting one at a time. And then lastly, it's important to, as you explore ways of optimizing your code, question some of the requirements that are there in the first place that both limit the amount of performance gain that you can have, but also in some cases, it's good to question and try to understand if your understanding of what the labels are supposed to mean and their confidence intervals are the same as your stakeholders and the same users. So in this case, one might argue that it's actually more correct to embed and predict at a paragraph level, because if I have 20 sentences that talks about one topic, and one sentence that talks about a different topic, do I really want that sentence to skew my result differently? And obviously it depends on what you're trying to do, but good to try and understand the reason behind those requirements. Some smaller lessons. So we talked about the importance of data cleaning and some of the thinking about some of those trivial questions, such as how to identify a sentence. We talked about how to parallelize using multiprocessing. We also talked about what C profile is and how you can interpret results from C profile. Thank you very much.